Welcome to MEI Numerical Methods, Approximating Functions. In this video we'll be looking at Newton's forward difference interpolation method. This is sometimes referred to as Newton's interpolating polynomial. Now suppose, for example, that we've conducted a scientific experiment and we've got some data points and we're interested in plotting a function to those points, and also it may be the case that we're interested in finding out what the value of the function is at some value of x in between the values for our points. So that would be described as interpolation. Now if we have just 2 points, then clearly we can draw a straight line through those points, and normally if we've got 3 points we can find a quadratic function that goes through them. So roughly like that. But of course, if the 3 points happen to lie on a straight line, then obviously that won't work. And in a more general case, if we've got n points, then we're going to need a polynomial function of degree n-1 to go through those points. Now here we have 3 data points which happen to lie on a straight line. Now this is a fairly idealized situation. Normally you'd have 3 points that were almost on a straight line and you'd be trying to fit a straight line through them, but for the sake of argument we'll assume they're lying on a straight line, and we're interested in finding the equation of that line. So the information can be recorded in something that's usually called a finite difference table. That's it's called finite difference to distinguish it from infinitesimal difference that you would get with differentiation. And so we've got for the point 4,8, we've got our x value there and the value of the function there. Similarly for the other two, and we're noticing that there's an increase of 3 each time. So as x increases by 1, the function increases by 3. So we can see that the formula is going to be, we're going to be starting with 8 and then adding on 3 for every 1 we go up by. So 3 is the gradient, and so we've got this formula here for the straight line. And we can check that that works by plugging in those 3 points if we wanted to. Now we can extend this to the case where we have an increase in x of 2 each time, so that our function is now going to increase by 6 every time x increases by 2. And the gradient of the straight line is 6 over 2. So for every 2 that we're increasing x by, we're increasing the function by 6. And then we can extend this to the simple linear version of Newton's interpolating polynomial, where we've got f0 is our starting value for the function, and delta f0 is the increase in the function from f0 to f1. So delta f0 is f1 minus f0, and then the letter h is normally used for the increase in x, which has to be the same each time. So that's h equal to 2 there. And in the next video we'll be seeing how we can extend this to higher order polynomials. So that concludes this video on Newton's forward difference interpolation, and we'll be carrying this on further in the next video.